Hello and welcome to this short demo of the new 3MF Beam Lattice extension functionality that can now be used with Polygonica. First, a little bit of background. Polygonica is a component software library that's written in C with API support for C and C#. It's widely used in a range of additive manufacturing software by vendors such as 3D Systems, Stratasys, Desktop Metal, Envision Tech, and Ansys, as well as in a range of other industries. At the request of a number of our customers, we recently added some unsupported example code to support 3MF reading and writing to and from Polygonica. You can find out about that in the previous video. If you're watching on YouTube, click on the top right of this video to find it. As always, short plug for our LinkedIn pages. You can follow Polygonica and MachineWorks Limited on LinkedIn, and we'd encourage you to do so, as we'll be push out all the latest updates, both large and small, through those channels. So what is the 3MF Beam Lattice extension? Well, it's an optional extension to the 3MF specification that allows lattices comprised of beams and nodes to be described parametrically, rather than in the explicit polygon mesh form used for the core of 3MF. By parametrically, we mean that a beam is defined as a start point and an end point, and two radii. If the beam is a cylinder, then the radii are equal. The radii are not equal, the beam is conical. The beam can also have flat, spherical or hemispherical end caps. Similarly, nodes where beams join together are just defined as a center point and a radius. The 3MF spec allows the definition of multiple different beam node lattices in a 3MF file, and interestingly, it also allows each lattice to be clipped against a specified mesh geometry. In the diagram below, you can see a small section of lattice and a sphere representing a clipping mesh. The three available clipping modes are shown below. None means the lattice is unchanged. Inside means the portion of lattice that intersects with the volume inside the sphere is retained, while outside means that portion is removed and only the lattice outside the sphere is retained. Beam end caps can be planar, what 3MF terms is but, spherical or hemispherical. Note that the images show a conical beam where the radii at the start and end points are different. Nodes are simply represented as spheres. An important point to watch out for is that the center point of the node definition must coincide with the endpoint of a beam. So how does the new sample code interpret this definition in Polygonica? Well, first a small reminder that this code is unsupported, and whilst you can use it out of the box, you might well want to adapt it so that it's optimized for your own specific workflows. The current Polygonica API has no parametric definition for beams and nodes. API functions are provided to create cylinders, spheres, cones, etc., but once they are created, they exist in Polygonica as a general polygon mesh like any other. If you want to retain the original parameters, you will need to do this in your own code. The 3MF import code creates a minimal set of meshes, or PT solids, that are required to represent these conical shapes. Then each actual beam or node is represented as a PT world entity. Think of a world entity as an instance of a mesh with its own transform and colors, etc., etc. In particular, the import code uses anisotropic scaling to grow and stretch the instance mesh so it is the desired shape. This heavy use of instancing means memory is saved until you want to convert the implicit lattice to a full explicit lattice structure. So let's have a look at the code for a second, and you can see the structure on the left is the general structure for transporting 3MF build items and lattices. There's a list of mesh solids as PT solids and a list of build items as PT world entities. Imported lattices are added to the mesh lattices array as a PG3MF mesh lattice. The parametric lattices are used for export only. On the right, you can see the structure of each mesh lattice, which has a list of world entities for beams and a similar list for nodes, plus an optional reference clipping solid. For export, the application must create a parametric representation using the PF3MF parametric lattice structure. This has a positions array of 3D coordinates, and a beam and node positions are indexed into this array. You can also see the structure for a parametric beam below, with a start and end radius, a start and end position indexed into the main positions array, and information about the type of the start and end caps. So let's firstly fire up Polygonica demo. First thing to say is this is a graphical user interface that I'm using. It's just a demo that's built using MFC on top of the Polygonica libraries. You can't buy it anywhere, and we don't give it out to customers or evaluees. So let's start by loading in the standard Beam Lattice examples from the 3MF GitHub. So let's open the pyramid model first. So the pyramid model here is entirely beams and nodes. There's no core mesh geometry included at all. So the 3MF file is really small. It's only 5 kilobytes, and it took about 0.4 seconds for Polygonica to load it in and union all the beam and nodes geometry together. You can see there's a range of beam radii with thicker beams at the bottom and thinner ones at the top. Now let's open up the next one. It's variable Voronoi. Again, this one is mainly beams of variable radii. You can see it all around there. But if we have a look at the top view, we can see that it's square. And this file actually includes a cuboid clipping mesh, which is used for clipping the lattice, but doesn't appear in the final build result. So in this case, we've used the Polygonica Boolean both to union together all the beams to create the lattice, and then to intersect the beams with the clipping mesh to create the clipped result shown on screen. And that was done in like 1 and a bit seconds. And finally, from the 3MF examples, there's this spinal implant model. So this model contains a reasonably complex mesh model and 3 lattices comprising over 35,000 beams in total. So it takes a little bit longer than the other ones to load in, but still around 10 seconds, as you can see there. That's pretty fast if you consider all the work that's needed to create a closed watertight manifold result from the large amount of parametric data. And this load time is relevant to one of the claims made about the 3MF Beam Lattice format, that it allows very lightweight files. So we're going to investigate this a little bit further. So we'll first save this file out as an STL. Save that. And then we're going to save it again in Polygonica's own PGS format. So there we go, saved down. And then if we have a look briefly here, we can see that the original 3MF is 256 kilobytes compared to the 38 megabytes of the STL and the 61 megabytes for the PGS. So just to explain the reason why PGS uses more disk space than STL is that PGS represents vertex coordinates in double precision, whereas both STL and 3MF are using single precision. So as an aside to this, we remain amazed that people still define file formats using single precision when double precision is available and disk space is plentiful and cheap. There are so many problems that can be avoided by staying within a higher precision workflow and not converting down to single precision. In fact, the 3MF specification does allow for double precision coordinates, but I'd bet if you create a double precision 3MF file, you'd have a hard time finding an application that reads it correctly. Anyway, there's no doubt that the beam node lattice size in the 3MF file is impressively small, but what impact does that have on load speed? So let's see how long it takes to load the STL and PGS files in. So firstly, let's go back. We'll open the STL. You can see that takes just over a second. And if we load in the PGS, see that takes around between half a second and a second to complete. So compare that to the original 10-ish seconds that it took Polygonica to create the explicit union geometry, and believe me, Polygonica's mesh Boolean is very, very fast. And I've summarized these results in a slide that you can see here. So there are swings and roundabouts here.
storing geometry in parametric form makes a lot of sense, but there are downsides. It's not a panacea. It really depends on your downstream workflows. Okay, so that's enough about import. Let's try something a little bit different. We're going to try creating a Beam Lattice in Polygonica demo, exporting it, and then loading it back in. So we're just going to create a simple sphere, and then we can save it with a Beam Lattice. We'll just accept all of these defaults that you can see here. We shall hollow the sphere, create an 8x8x8 diamond lattice, and save it out to 3MF. So click on that. We'll overwrite this one that I've done as a test. See, that took about 0.2 seconds, as all we're doing is saving start and end points and radii. So let's load it back in. And Polygonica has to do a bit of work here to convert the parametric beams to an explicit mesh structure. So you can see that takes a similar amount of time. So you can see it took about 6.3 seconds there. So now if we turn transparency on, and we'll just change the view so we can see. So you can see there that the sphere has been hollowed out and the diamond lattice is added to the interior. And if we go back to the original sphere and turn transparency on, you can see that that's not hollowed and there's no lattice. We've hollowed a copy and we never actually created any explicit lattice as part of the export process, only an implicit parametric one. But you don't have to make the mesh explicit on import. For example, we can load it in and slice it, as explained in our previous video, slicing and 2D profile operations, lattice creation. So let's close these spheres down. Don't want to save that. And now we'll create a new window, and then we'll load the file in using load and slice, which will create 100 slices through the file from the instance world entities without needing to do a full Boolean first. So go load and slice, sphere, let's open it back up. So let's just switch to the top view, and you can just see that you can see the grey sphere there in this window. That isn't the geometry from the 3MF file. It's just some reference geometry that I've created so that my mouse has something to rotate around. If I zoom in, you can see the lattice slices have been correctly clipped to the edge of the hollow sphere, but done in 2D on a per slice basis rather than in 3D. Just have a quick move around, you can see all there. Right, so let's round trip this with one final model. So we're going to load in this gear knob STL. We can see that it's typical of some surface models. The orientation is inconsistent and there are gaps between the different surface patches. So we're just going to give this a quick auto heal using Polygonica. And now that everything's good, so let's export it to 3MF with a lattice. Same again, using the 8x8 diamond lattice. We'll overwrite the example one that I've done. And then we'll load it back in. Okay, 8. See, that took around 9-10 seconds. I'm going to make it transparent. We're going to flip to the top view. So we've got a nice look through it there. And you can see that the clipped lattice is correctly union to the hollowed out part there. Let's have a quick look around so you can see all from different angles. So thank you very much for your time for watching this demonstration. If you have any questions or you'd like to know more, then please don't hesitate to get in touch with us, either using our LinkedIn pages or using the forms on our website. Thank you very much for listening.